Hi guys, tonight we're going to continue to look at geometric sequences. We reviewed geometric and arithmetic sequences last night, and tonight we're just going to focus on the geometric sequences. So let's go ahead and get started. So we're back to our brown tree snake from class the other day. So here is the sequence again for the brown tree snake. This is the year 0, this is where it begins, 1, 2, 3, 4, and the number of snakes. So at year 0 we started with 1 snake, and to year 1 there was 5, and to year 2 there was 25, then 125, then 625. And keep in mind that time is our x, an independent variable, and the number of snakes is our y, or dependent variable. So as we read yesterday, the brown tree snake was first introduced in Guam in year 0. At the end of year 1, 5 snakes were found. At the end of year 2, 25, and so on. Using the table of information, a graph can be drawn where y is the independent variable, or where year is the independent variable, and the number of snakes is the dependent variable. So how is this graph different from our last unit? So our last 2 units we focused on linear equations, and this graph is nonlinear, and specifically this graph is curved, and there is a name for that curve, and we'll talk about this in the unit. This problem situation, this curve or this graph, is known as an exponential function. And exponential functions increase or decrease very quickly. And that's how we get this curve shape right here. So this particular function is a growth function, which means the tree snake population is getting bigger. And with a growth function, the common ratio is always bigger. It's bigger than 1. Because if the common ratio is 1, then nothing's changing, and if the common ratio is between 0 and 1, then that means that the snake population will be getting smaller. But today we're going to focus on growth functions or increasing sequences. So let's look at a similar population growth for a certain kind of lizard, and we're going to look at the table, and we're also going to look at the graph. And we're going to use either the table or graph to answer the questions below. So at this point, if you want to stop the video and answer the questions yourself and then go back and check to see if your answer is correct, that's a good idea. If you're not so sure, then you can just hang out with me. So the shape of the graph, notice in the shape of the graph that the information is exponential in nature. And how do we know it's exponential? Because it's increasing quickly, and this is at the growth of the lizard population. So the first question, we want to look at the graph. What does the information from the point 240 on the graph tell you? Well, if we look at the table, we know that the x value is measuring the year, and we know that the y value is measuring the number of lizards. So if we're going to go over to the table and go find the point 240, which is right here. Here's the point 240. That's this point right here. That tells us that after 2 years, because x is measuring years, it tells us there are 40 lizards. And we can tell that from the graph, which is right here, and we can also tell that from the table. After 2 years, there's 40 lizards. What information does the point 120 on the graph tell you? So again, here's the point 120 right there. Same thing, x is measuring the years, and y is measuring the number of lizards. So this tells us at the end of year 1, or after 1 year, there are 20 lizards. So linear or not, or exponential, we can still get information from the points, and we can get information from the graph. So question 3 on the next page of your notes, I'm just going to leave it up here for a second, asks, when will the population exceed 100 lizards? So we want to know, when will the population of exceed 100 lizards? So here's 100. We want to know at what time is it going to be more than 100. So if here's 100 lizards, somewhere in between year 3 and 4, that population is going to get up to past 100. So here's 100. It hits that red line somewhere about 3.5 years. So like we saw on the graph, when will the population exceed 100? And it's going to exceed 100 between 3 and 4 years. So now we want to find the common ratio using either the table or the graph. And last night we talked about using consecutive terms and dividing the following term by the previous term. So I'm just going to pick, for our lizards, I will pick the last 2 terms. So I want to know, what do I have to multiply by 160 to get 320? And so I get 2 because 320 divided by 160 is 2. I could do the same thing with the other terms. 20 divided by 10 equals 2. 40 divided by 20 equals 2. So our common ratio is 2. If the information from the table were written as a sequence, what is the initial term? So where are we starting? Where is our start? And the initial term, our A1, is at 10. So how can we find the 10th term in the table, graph, or in the sequence? So the graph does not go up to 10, up to 10 years, or the 10th term, or in this case. So we can just keep on multiplying the sequence by 2. So if we ended up with 320, that was our 5th term. Then our 6th term is 320 times 2, which is 640. Our 7th term is times 2, which is 1,280. Our 8th term is 1,280 times 2, and that's going to give me 2,560. Our 9th term, if I multiply 2,560 by 2, is going to give me 5,120. And then my 10th term, if I multiply 5,120 by 2, I'm going to get 10,240. So our 10th term in the sequence is 10,240, and in this case, it's lizards. And again, to do this, we multiplied times 2, times 2, times 2, times 2, and times 2. Okay, so last scenario, let's take a look at the mice problem. And I suggest you pause the video at this point and then go ahead, work this out yourself, and then come back and check your answers. But if you're not sure, you can go ahead and continue through this problem with me. So a population of mice has a growth factor, also known as the common ratio, because it's growing. So the growth factor and common ratio are the same thing. And that common ratio is 3, so our common ratio is 3. After 1 month, there are 36 mice. After 2 months, there are 108 mice. So at the end of month 1, there's 36. At the end of month 2, there's 180. No, there's not. There's 108. Sorry. So if it has a growth factor of 3, or a common ratio of 3, then that means we are just multiplying each term by 3 to get to the next term. So after 3 years, there'll be 324. 324 times 3 is 972. And then 972 times 3 is 2,916. So how do we work backwards to get this number? Well, what can I, that's question number 2. How many mice were in the population initially at 0 months? So how can we get this number? Well, we know that the growth factor, if we do 108 divided by 36, we get 3. So what number can I multiply or divide or multiply times 3 to get 36? So to find our initial term, our A1, all I have to do is 36 divided by 3 equals 12. So our initial term is 12 because 12 times 3 equals 36. And that's the term we have right here. Is this sequence arithmetic or geometric? And explain how you know. Well, we said it had a growth factor and a common ratio, therefore it must be geometric. Because you multiply to get to one term to the next. And that's going to create eventually some really big numbers. Number 4, is the graph of the table going to be a straight line or a curve? Well, we talked about that. Because it is geometric, that means it's going to be a curve, because it is increasing exponentially. So we're going to graph the table to make sure your answer, we're going to graph that table here on the graph to the right. Make sure you label and title the graph below. So the graph is not below, the graph is to the right. So our x-axis is our independent variable, and that is measuring the months. Our y-axis is the dependent variable, and that is the number of lizards. Sorry, we are on mice now. And we can title this the mice problem. So we have our scale on our x-axis. Because our numbers are increasing so quickly, our scale on our x-axis is counting by hundreds. So 100 is here, 200, 300, 400, 500. And the scale, sorry, that was the scale on our y-axis. And the scale on our x-axis is just increasing by ones. 1 month, 2 months, 3 months, 4 months, and 5 months, because that number is not increasing too rapidly. So now we want to go ahead and graph this. So we need to graph our first point at 0 months. We started out with a mouse population of 12, so that's going to be something kind of all the way down here. At 1 month, we had a mouse population of 36. At 2 months, it was 108. At 3 months, it was 324. And again, we're estimating where our dots go. At 4 months, the mice population was 972. So here you can see where it's starting to increase. And then at the end of 5 months, the mouse population was 2,916, which on our graph is all the way up here. So if we connected this, we would get this curve right here, and this is called an exponential curve because it's increasing quickly, and we have to multiply to get to one term to the next. So here are your 2 Google form questions. Looking at the table below, we can determine, is this an exponential function? Is it a linear function? Do we not have enough information? Or it could be either an exponential or linear. So again, you want to take a look at the shape of the graph. Is it an exponential function, which curves, or a linear function? Question number 2, use the example below. What is the common ratio for the geometric sequence? Please be sure to write your answer as a whole number or decimal. So this one, when we're looking at the common ratio, we need to look at this column right here. How do I get from one term to the next? So our sequence in this case is 300, 150, 75. how do I get from 300 to 150, 150 to 75? Be sure to put your answers in on the Google form. And again, if you have any questions, you can ask those on the Google form as well.